In this lecture, my goal will be to explain to you the sometimes confusing concept of voltage, which arises in electricity and electric fields. Now, electric fields themselves are not intuitive, and that's exactly what makes voltage so confusing. Now, instead of finding voltage for electric fields, I'm going to first see if I can find a similar concept of voltage for gravitational fields. In other words, does such a concept for gravitational fields exist? And if I find that, I can then have a better understanding of what voltage is for electric fields. And that's because we have more intuition about the way gravitational fields work. So let's begin by looking at gravitational potential energy. Now recall that gravitational potential energy is a state function. And to illustrate what a state function is, let's look at the following example. Suppose we have a block of some mass m at some height 0. So the block is positioned on our ground. It's on the surface of our Earth. Now suppose we move our block up a height h. So we move our block from initial position of h0 to final position of height h. And I do this in 3 different ways. I follow 3 different pathways. In my first pathway, I drag my block up in this path. In my second pathway, I drag it up exactly straight up. So this is the most direct path. And then I follow a third pathway, dragging my block in this path. And I get to the same position. Once again, in each path, our initial and final positions are exactly the same. They're identical. And now I want to ask the following question. What is my gravitational potential energy for each pathway? In other words, does each pathway give me a different gravitational potential energy? So to explore this question, let's look at the formula for gravitational potential energy. The formula, as we saw from a previous lecture, is the potential energy due to gravity, or gravitational potential energy, is equal to force of gravity times our h, times the distance up. So our distance up equals to force, we know, is simply our mass of the object times our gravitational field g. So m times g times h. Note that because our initial condition is h equals 0 in both cases, and our final condition is h in both cases, or in all 3 cases, that means that my gravitational potential energy for all 3 pathways will be the same exact thing. So that means that gravitational potential energy is independent of my pathway taken. And that means it must be a state function. And that's exactly what a state function is. A state function is a property such that is independent of the pathway taken. It only depends on the initial conditions and the final conditions. Now, I want to ask the following question. Does a function like gravitational potential energy exist that's independent of mass? So that's independent of pathway and independent of mass. And the answer is yes, it does. Now to see what it is, let's look at this picture of our Earth. So here's our Earth, here's our surface, and this height h is simply some height h above our ground. So this orange outer dashed line represents the height h around the entire Earth. So my question is, well, if I take some mass and I raise it up this height, I will get, or I could find, my gravitational potential energy using this formula. But I want to ask the question, does some function exist that will give me my potential of my field regardless of my mass, independent of my mass? And the answer is yes, it does exist. And it's g times h. G is simply my gravitational field, and h is the height. And if I simply multiply the two, this guy will be independent of my mass. So, if I simply take my g and multiply it by my h, I will get the potential of my field, and this is independent of m. And now if I want to find my gravitational potential energy, I simply take my potential of my field, g times h, and multiply it by m. Now this guy is simply known as the gravitational potential. Not the gravitational potential energy, but simply gravitational potential of the field, of the gravitational field at some height h. And this gravitational potential is independent of m. And it's given by g times h, or the gravitational field g times some height h. And this is exactly what is known as voltage, except this voltage, this gravitational potential, is for gravitational fields. So now I want to ask the question, can we find a similar concept for electric fields? Not for gravitational fields, but for electric fields. And does such an electric potential exist? Remember, we already spoke about gravitational potential energy, and we compared that to electrical potential energy. Now I want to see if gravitational potential exists, does electric potential exist? And the answer is yes, because electric potential is simply what we call voltage. So let's see. So let us finally examine what the voltage is when we talk about electrical fields. Now we just said that in order to find the gravitational potential energy, we take our gravitational potential and multiply it by our mass. In other words, we take our mass of some object, multiplied by g and multiplied by d, where g is my gravitational field at the surface of the earth, and d is my distance above the earth. In other words, this guy's my gravitational potential. It's my potential of my gravitational field at some height d above the surface of the earth. So if I look at my earth, this is my blue earth, and this is my height h above my earth. So this orange line represents the gravitational potential at a height h above the earth. So this guy is independent of mass. And if we want to find the gravitational potential energy, or the energy required to bring a mass m from the surface of the earth to this height h, we simply take the mass m and multiply it by our gravitational potential at that height d, or that height h. Now let's compare this to our electric field situation. Let's try to find what our electrical potential is for electric fields. Well, to find our voltage or electrical potential, we look at what we did here. What did we do to find the gravitational potential? Well, we simply took our g, our gravitational field, and multiplied it by the distance d. That's exactly what we should do for electrical fields. We take our electric field E and multiply it by my distance d, where this is my positive charge and this is my distance d above this charge. And so this line represents my voltage or electrical potential of this field. The potential that is in this field when it's a distance d away from this charge. So this is my electrical potential. And notice that it's independent, not of mass, but of charge. Because when we're talking about voltages in electric fields, we're talking about charges and not masses. And so, finally, to find the electrical potential energy, we follow the same steps that we took to find the gravitational potential energy. So we simply take our gravitational potential and multiply it by mass. So that means we take our electrical potential and multiply it by some charge Q1. Now notice this charge Q1 is not the same thing as this charge Q. Let's say this charge is capital Q. This charge is Q1 is simply some random charge that we're bringing from an infinite distance far away to a distance d away from our large Q. In other words, this energy gives us the amount of energy that we need to input to bring that charge, that positive charge Q1, a distance d close to this positive charge. In the same way that we said, this energy gave us the energy that is required to bring this mass from the surface of the earth to this height h. And we simply multiply it by our gravitational potential. So you see, these two guys are analogous. It's just here we're talking about one type of field, a gravitational field, and here we're talking about a second type of field, a electric field. Now one last thing I want to mention. The reason that we're bringing a charge from an infinite distance far away is because if we take a positive charge an infinite distance far away, if we're talking about an infinite distance, that means this r is infinity. So some number over a very large number makes our force zero. If force is zero, energy is zero. So a distance infinitely far away for this Q1 experiences a force of zero. And that's exactly why we're bringing that guy from infinity far away to this distance here. Now one last thing. Notice that just like for this case, this line, this orange line, represents the same gravitational potential. In other words, at every single point on this orange line, we have the same gravitational potential. Just like on every single point on this electric potential line, we have the same exact value for our electrical potential, or our voltage. And this line is called an equipotential line. And we'll talk about them in another lecture.